I'm going to discuss the potential that's felt outside a polarized dielectric. As a side note, this actually can be used to examine the potential inside a polarized dielectric, but I'm not going to talk about that in this video. So I'm going to start simply by giving you the result, so we know where we're going. At a point R1 outside a piece of polarized dielectric, so let's just draw a polarized dielectric here and assume there's some kind of polarization P is given by the following formula, and we'll justify and derive this over the course of this video. So we've got a surface integral of sigma P, that's a charge density, a surface charge density, 4 pi epsilon naught R12 dotted with, no not dotted with, dA2 plus the volume integral of rho P over 4 pi epsilon naught R12 dV2. And so what that means is that we're going to consider little volume elements here. This is dV2 at a position R2, and little surface area elements here, dA2. And there's some kind of charge density that arises from polarization that gives rise to a potential outside the dielectric. I just realised this R looks a little bit like a sigma, so I'm going to replace it. Now, how do we get there? Why does this happen? The first thing to do is just to note the definition that this is P, it's a capital P, as the polarization, and it's defined as a dipole moment per unit volume. And physically what's happening is an electric field is applied to a dielectric material. That's an insulator of some kind. It could be glass, it could be plastic, it could even potentially be wood. And the positive nuclei respond to a field in the opposite direction to the negatively charged electrons. That's true. The little pictures you sometimes see in textbooks of little circular clouds of electrons around the nuclei is an oversimplification and bears no resemblance to the full quantum mechanical simulation of what's going on in the material. The key thing to realise and remember is that electrons move in an opposite direction to the positive nuclei. And that gives us a polarization, it gives us little dipole moments all over the material, and so we can treat it in that way. So let's just see how we get to this potential. So in general, if you have a charge density, then this is the kind of formula is the standard approach to it. It's just that in this case the charge density is down to the polarization. So let's just think about integrating over our material over here, and we're going to think about a little volume to start with. So if we think first of all about the potential due to a small volume, that's going to equal delta V, that's going to be the little volume at V2, multiplying the polarization, P at R2, and that's going to be dotted with R21, and we're going to divide by 4 pi epsilon naught R21 cubed. So this is just the simple formula for the potential of a dipole. We have derived that in a previous video. And note that we have delta V times capital P, that's effectively the dipole moment of this little piece of material. So let's just write that as P, the dipole moment, that's a little p. Of course, we're now going to integrate over the entire material. So when we do that, actually let's just say that we've got a delta V there to indicate as a contribution. So V at R1 is the volume integral of P at R2 dotted with R21 divided by 4 pi epsilon naught R21 cubed dV2. That's just integrating over the entire material. It doesn't really tell us very much. So the first thing we're going to do is we're going to remember the gradient, the grad of 1 over R21, which is, as it turns out, this little formula here, R21 over R21 cubed. And we're also going to use the vector identity, the divergence of a scalar multiplying a vector is given by the gradient of the scalar dotted with the vector. And what we have here is the gradient of a scalar dotted with a vector plus the scalar multiplying the divergence of the vector. So when we do that, we substitute those two results in. We see the following. So first of all, I'm going to write, we've got a capital P at R2 divided by 4 pi epsilon naught R21. No, not R21 cubed. I'm going to leave the 4 pi epsilon naught there. And then we're going to have that dotted with R21 over R21 cubed dv. And that is just, okay, let's pull the 1 over 4 pi epsilon naught outside. Volume integral of P at R2 dotted with the gradient of 1 over R21 dv2. And that's the gradient with respect to R2. Now, using the vector identity we've just shown, we can rewrite that one as it's going to be the divergence of the product of the two minus the scalar multiplying the divergence of the vector. Let's write that one out just to be clear. We've got a 4 pi epsilon naught, we've got a volume integral, and we have the divergence of the vector p divided by R21 minus 1 over R21 multiplying the divergence of p at R2. P of R2 here, and that's a dv2. And now what we're going to do is use the divergence theorem on this first part here. And remember that the volume integral of a divergence of a vector can be written as the surface integral, the closed surface integral of that vector over the surface. So we find V of R1 is, let's bring the 4 pi epsilon naught back inside now. So we've got a closed surface integral of P dotted with N dA2 divided by 4 pi epsilon naught R21 minus the volume integral of the divergence of P dv2 divided by 4 pi epsilon naught R21. And if we wanted to, we could bring the minus sign inside that volume integral. And so we have a closed surface integral of P dotted with N over 4 pi epsilon naught R21 dA2 plus the volume integral of minus div P over 4 pi epsilon naught R21 dv2. And if we look back at the result I showed you just at the top here, we have the surface integral of the surface charge density, the volume integral of the volume charge density. So we can see that we can identify the following. Sigma p, the surface charge density, is P dotted with N, and rho p, the volume charge density, is minus the divergence of the polarization. So this simply shows that if you have a material which has been polarized, a dielectric material where the charges have been shifted, there's a net charge density in different places in the material. Of course, the overall charge density the overall total charge remains zero, it's still a neutral material, but there's a charge density induced in different places by the polarization, which gives rise to an electric potential and hence an electric field. And this is why we've introduced the idea of the electric displacement, the field D, because it allows us to make calculations which don't involve the full complications of trying to understand the relationships between P and E. These charge densities that we've derived here are real. They actually occur in materials. We can see that, for instance, the volume charge density, so this implies that in a uniform material, in a uniform polarization, that gives zero charge density. And the surface charge density, if the polarization is perpendicular to the surface normal, then you get zero. So, for instance, one of the classic examples we have is a block of material And if we have a polarization which is along this direction of that arrow, then we will definitely have a charge density on the ends where the dot product between the polarization and the surface normal is 1, but we will have 0 charge density on the other sides where the dot product is 0. We can then go on and use this to calculate various situations, and I'll do some examples of that in another video. But that's where I wanted to go, just in terms of deriving these charge densities. It's simply just an acknowledgement that the application of an external field creates charge densities which then create new fields within a material.